Hello everyone, welcome to my channel Deep Tuition Class. In this video, I'll be starting the topic called Fundamental Theorem of Arithmetic from Chapter 1, Real Numbers. So as I have mentioned in the previous video that I'll be starting the topic Fundamental Theorem of Arithmetic. If you are new to my channel, please like, share and subscribe and hit the bell icon for more updates. So let us learn what is Fundamental Theorem of Arithmetic. So Fundamental Theorem of Arithmetic has got many names. Among those are Unique Factorization Theorem or Unique Prime Factorization Theorem. As in the previous class we have learned about Euclid division lemma. Alright, so it was the Euclid division lemma was dealing with the division method. Alright. Similarly, fundamental theorem will be dealing with the multiplication method. Alright, so what does this state? Let us learn. It states that every integer greater than 1 is either a prime or can be expressed in the form of prime. So now the new term is coming here is prime. So fundamental theorem states that any number greater than 1 is a prime or it can be converted into a prime number. Now the biggest question comes, what is this prime number? If the number is not a prime, what is the another name for the number? Alright, so let us see. So prime numbers from the lower class, we know that what is prime number. So if you don't have idea, I am clearing the term, that is prime number. So prime number are those number which can be divisible by 1 or can be divisible by itself. So example here I've given, just see 2, 3, 5, 7 and 11. So 2 can be divided by 1 or 2 should be divisible by itself, that is 2. It cannot be divided by other number like 3, 4, it cannot be divided, right? Similarly, 3 is another prime number, 5 is another prime number, 7, 11, etc. It will go on like this. Alright, so infinite prime numbers you are going to find. Alright, so prime numbers are those numbers which can be divisible by 1 or can be divisible by itself. Alright, so if the numbers are not prime, then what are the other term used for prime number? The other term is composite number. So I forgot to mention, so the smallest prime number is 2. Alright, so composite number, like for example 4, 6, just see the example. 4 can be divisible by 1, 4 can be divisible by 2, 4 can be divisible by 4 itself. So here how many multiples we are getting, how many factors we are getting? In prime numbers there were only 2 factors or 2 multiples, isn't it? But in composite number we can get more than 2 divisible or 2 factors or 2 multiples. Alright, 4 can be 6, similarly 6 can be divisible by 1, can be divisible by 2, can be divisible by 3. So here more than 2 factors are available to divide the number. So these numbers are called composite number. Alright, so I hope you are clear with this two term, that is prime number and composite number. So a fundamental theorem is nothing but a number can be a prime number, or if it is not a prime number, say for 4 is not a prime number, but we can express that number into a prime number, right? Say for example 35 is not a prime number, but we can convert that number into prime number. 7 into 5 is a 35. 7 is a prime number, 5 is a prime number, isn't it? So we can convert that number which is not a prime number, we can convert that number into a prime number. So this is nothing but a fundamental theorem of arithmetic. Once again I am repeating, it states that every integer greater than 1, say for example 4 is not a prime number, but that number 4 can be expressed in the form of primes. Alright, so using this concept, using the idea of this, we are going to solve exercise 1.2 which is based on this fundamental theorem of arithmetic. Alright, so let us start solving exercise 1.2. So this is the question from exercise 1.2. Number 1, express each number as a product of its prime factors. Prime factor means you have to do LCM. You have to express this number as a product of its prime factors. So let us start solving. Okay, this is your first question. So to solve this, we have to write by taking the LCM, isn't it? By taking the LCM, we will get the product of its prime by taking the LCM of 140. No? Whose we are taking? Whose LCM we have to take out? 140 LCM. So its prime factors we are going to get. So you all know how to do LCM, alright? So this is the way to do. 270, 235 ja, 5 7 ja, so 7 1 ja, 7, isn't it? So therefore we can write 140 is equal to 2 into 2 into 5 into 7, isn't it? So we can also write like this, 2 square, because 2 times 2 is there, so square we can write. So 5 into 7 is the prime factor. Alright. So now you understood this was not a prime number, but we have expressed this number in a prime number. So this is a fundamental theorem of arithmetic. Alright. So next question is number B, 156. Similarly, we will solve this also by taking the LCM of 156. We will get the product of its prime factor. The product of its prime factor. Alright. So similarly we have to take out the LCM. Start with the 2. Start with the smallest number, smallest prime number, that is 2. Not with 1. Okay. Not with 0. Boom. That is different case again. So we'll start with the 2. 2 7 14, 2 78, 2 3 6 1, 2 9. So here we can get 13. So yes, 3 we can start with the next. After 2 what comes? 3 is the next prime number. So 3 13. So 13 is itself a prime number. So 13 1. So 156 is equal to 2 into 2 into 3 into 13. You can multiply like this also. 2 to the 4, 4 3 is a 12, and 12 into 13 is 156. Alright. You can do direct method. If you don't want to do this, you can do directly this. So you can write like this, 2 square into 3 into 13. So all are prime number here. Itself they are a prime number, isn't it? So 3 is a prime number, 2 is a prime number, 13 is a prime number. So we have expressed all the numbers in a prime numbers. Alright. I hope you are clear with this. Similarly, we will solve numbers. Okay, here is our question, number C. So I'll solve with 3 because 2 is not possible with this. So I'm using another prime number, that is smallest number, that is 3. 3 it is. Okay, it is 1 2 7 5. Alright. Sorry for this. Again, 3 is possible. 1 2 7 5. Suppose 12. 6 1 425. 425. Alright. So again, if 3 is possible, we are going to use 3. 3 1 3 3 4. No, 3 is not possible. We will use 4 is not possible again. So 5 we are going to use 40 85. So 3 is possible here. 6, no. Second 5 should be possible. 5 17. 5 17. So 17 itself is a prime number. So we can write, you will write this statement here. Alright. By taking the LCM of 3 and 2 5, we will get the prime number. So I am directly writing this here, that is 3 into 3 into 5 into 5 into 7. So we can write 3 square into 5 square into 7. We'll count only 1 3, 1 5 and 1 7 because we are finding the prime number, prime fact. We are getting the prime factors, isn't it? So fundamental theorem this is. Alright. So this is our next question. So similarly we will write this one by taking the LCM of 5005. We will get the prime factor over here. Alright, so that is your work to do. So we will get that prime factor first. Okay, how to which number we are going to use? 3. By looking at the end of this digit, unit digit, we shall try 3, but no, 3 is not possible. So we are going to try another number, another prime number, that is 5. So 5 1s 0 0 5 1s. Alright, so here we are going to use the number 5 is not possible because at the end there is 1. So 3 is also not possible, so we are going to use 7. Let's try with 7. 7 1s 7 0 7 1s 7. Okay, so okay, yeah, 143. Yes, and answer. Yeah, all right. So next we have 7. No, 7 is not possible. 3 is not. So we'll try with 11. 11 13 is possible. So 13 1s is the answer. Alright, so 5005 can be written as 5 into 7 into 11 into 13. Alright, 11 into 13 is 143. 5 cents are 35. 35 into 143 is 5005. So this is our prime factor. Alright, so let's move on to the next question. So similarly we will write here by taking the LCM of 7429, we will get the product of its prime factor. Alright, so we can write hence 7429 is equal to, let us take out the LCM 7429. Okay, so let us try with 3. So looking the last unit digit, the possible values we can use are 3, but 3 is not possible. I have tried. So another 4 is not possible, 7 is also not possible, and 9 is also not possible. So directly we are going to jump in 17 table. Alright, 17. So it is 17. It is 437. Alright, so again to solve this, looking at the unit digit, we can use 7, but 7 through 7 it is not coming. 3 also it's not possible. 9 3 no, it's not possible. And we can use 19 here. Yes, 19 is 23, and 23 is a prime number, so 23 1s. Alright, so our prime factors will be 17 into 19 into 23. Alright, so this will be our prime factors. Alright, so into 1 also you can write, but it is simply like this: 19 into 23 1s is 23 only, no? So the value won't be changing. So 17 into 19 into 23 is the prime factor of 7429. Alright, so I hope you are clear with this. We have solved using the fundamental theorem of arithmetic. Fundamental theorem of arithmetic was stating that any number greater than 1 can be prime number, or that can be expressed in the prime number. Alright, so this was not a prime number, but we have expressed this number in a prime number. So this is nothing but a fundamental arithmetic of theorem. Alright, okay, next we have is 510 and 92. So we have to express 510 and 92 as the product of its prime factors. So 510 should be expressed in the form of, it is 255. After that 3 is not possible, 5 is possible. 5 5 is 25, 5 into 5. Then 3 is possible, 3 17 and 17 1. 17 itself is a prime number, so we can express this in 2, 5, 3 and 17. Alright, so next we have 92. 92 we can express 246, 223, and 23 is a prime number, so no one can divide it. Itself can divide, so 2 into 22 into 23 into 1. Okay, so this is the condition. So if you have to find the HCF, I am here finding the HCF. So highest common is this, the number which is repeating is 2, and the LCM of this is 2 into 5 into 2. 2 here, 1 2 I am writing here, 5 2 3, after that 23, then 17 into 1. Also 1 also you can write the HCF, but 2 1s is 2, so I have directly written the answer. So after the multiplication you are going to get the number 23460. Alright, so this is our HCF and this is our LCM. Okay, so now what we have to do, we have to get the product. Now product of 510 and 92 is equal to 510 into 92 is equal to 46920. Alright, this is our product. And now product of HCF and LCM. Product of HCF and LCM is equal to, our HCF is 2 and LCM is 23460, 0 12 9 6. Okay, so you can see the product of 510 and product of HCF and LCM is getting matched, so we can write hence LCM into HCF is equal to product of 510 and 92. Alright, so this is verified again. Alright, so similarly we will solve for number 3 also. So similarly we will solve this, expressing 336 and 54 into its prime factor. 336, let us write the LCM first. So it is 2, so it should be 2168, and 2 8 is 16, 284, 242, similarly 221, 3 7 is 21, 7 1 is 7. So when we have to express this 336 into its prime number, we'll write 2 into 2 into 2. How many? 1 2 3 4, 4 and 3 into 7. Next 54. 2 27 is 3 9 is 27, 3 3 is 9, 3 1 is 3. So you can write 1 also here. So it is 2 into 3 into 3 into 3. 2 3 is 6, 6 3 is 18, 18 into 3 is 54. Okay, so now our HCF is 2 here. So this 3 is also getting matched and 1 is getting matched. So we can write 2 to the 4, 4 is the HCF. Alright. Oh, extremely sorry. 3 was getting matched, so 2 3 is 6. Alright, so 2 3 is 6. And our next is LCM. You have to find the LCM. So 1 is here 2, 1 is here 3. So now the remaining one, whatever is there, 1 2 3. Okay, 3 2, 1 2 3, 1 2 3 we have written. Now the remaining 2, 3, 1, 7 and 1. What should be the LCM? The LCM should be, it is 3024. Alright, now we got our HCF and LCM. Now what we have to do, product of 336 and 54 is equal to, product is, when you multiply this two number, we are going to get, it is 18144. This number I have already multiplied, so I am writing directly the answer. Similarly, product of HCF and LCM, or LCM and HCF, is 6 into 3024. It is okay, it is 18144. So therefore LCM into HCF or HCF into LCM is equal to product of 336 and 54. Alright, this is verified. Alright, I hope you are clear with this.